Hey everyone, welcome to the MCP from Zero to Hero series. Before we get into the nitty gritty of the full course, I want to kick things off with a real time demo so you can see MCP working in practice. Right, let's jump straight in. Imagine I'm a product manager and I type, I need to create a PRD, which is a product requirement document for an AI powered baby tracker app. The app should help parents track feeding times, sleep patterns, nappy changes, and growth milestones. It should use AI to provide insights and predictions about the baby's development. The target audience is the first time parents, and we want to emphasize ease of use and peace of mind. As soon as I submit this request, you will notice the agent immediately detects the available tools from Atlassian MCP server. It then starts generating a PRD in a prd.md file. In just a few seconds, we have a comprehensive product requirement document for our baby tracker app. But that's not all. Let's take it a step further. Suppose I ask the AI, can you refer to the software development template available in my company's conference workspace? The agent will connect to our Atlassian account, locate the relevant product requirement template, and use it as a reference. Next, the agent triggers a tool from Atlassian MCP Server called the Conference Search. It searches the Atlassian Conference workspace for a few pages relevant to my query, along with the associated metadata. Then it runs another tool called the Get Page to fetch the full content. After a brief moment, the agent confirms, I have successfully created a new conference page for your baby tracker app. Here's what I've included. If we refresh our conference workspace, we will see a new page titled Product Requirements AI Powered Baby Tracker, complete with objectives, problem statements, target audience, user personas, and success metrics. What's especially impressive is that the agent formats the tables and sections to match conference template, not just plain Markdown. It converts the drafted content to align perfectly with the company's formatting standards. Here's what we will cover in today's episode. First, I will introduce what MCP is, why it matters, and highlight its key features and benefits. After that, we will set up our development environment together and create your very first MCP server. I'll explain the core building blocks of MCP, tools, resources, prompts, and context. This is a hands-on project, so we will dive right into building a conference MCP server from scratch. Then I will show you how to integrate it with VS Code, Copilot, and Claude Desktop. MCP stands for Model Context Protocol. It's a standardized way for AI models to communicate with various tools and services. Think of it like a universal USB-C connector for AI applications. One standard that really works regardless of which AI model or tools you are using. Just like a USB-C lets you connect the same cable to different devices, MCP makes your AI integrations portable. You can easily swap out one AI model or client for another without having to rewrite all your code. This modularity means you spend less time on custom integrations and more time building features that really matter. And because MCP is a standard, it means everyone integrates with large language models in the same way, instead of writing custom one-off code for each new model or tool. Plus, MCP helps future-proof your projects. As new AI models and the tools emerge, you can plug them into your existing setup with minimal changes. Just like plugging a new device into a USB-C hub, this flexibility and the simplicity are what makes MCP so powerful. Let's take a moment to explain how MCP works, especially in the context of one of the biggest recent advancements in AI, function calling. Function calling is a breakthrough that's enabled large language model to use tools and APIs, much like how humans use tools and extend their abilities. In human history, one key difference between us and the other primates is our ability to understand and use tools. The same principle now applies to the LLMs. Here's the basic idea. In programming, you define the functions or methods that to perform specific tasks. With function calling, you can provide these function definitions to an LLM. When you send a query, the LLM decides whether it can answer directly or if it needs to use a tool. If a function call is needed, the LLM returns an action indicating which function to call and with what parameters. The actual function, tool, or API is then invoked by your application. Just to note, it's not invoked by LLM itself. The result is passed back to the LLM, which uses it to generate the final response for the user. While function calling is powerful, it often requires custom code for every new tool, API, or authentication method, and can become complex as you scale. This is where MCP comes in. MCP standardizes how tools are defined and accessed by LLMs. Instead of writing custom integration code for each new tool or API, you configure tools on an MCP server. Each MCP server can represent a service provider with a collection of APIs. The LLM simply decides when to use a tool, the MCP server handles the rest. Tool invocation, authentication, and response formatting. This approach means you don't have to reinvent the wheel every time you build a new AI application. You just need an MCP client that can talk to an LLM or multiple LLMs and handle responses while the heavy lifting is managed by the MCP server and the service providers. The portability and the extendability of MCP have been clearly demonstrated in just the last 6 months since its creation in November 2024. Thousands of MCP servers have already been created and shared across the internet. Several third-party MCP registries now host more than 10,000 MCP servers, covering a wide range of use cases from data and file systems, development tools, web and browser automation, productivity, and communication. There are also official integrations available. If you check Anthropic's official GitHub repository, you will find a number of service providers that already offer official MCP servers. Okay, now it's time to get our hands dirty. There are no prerequisites for these sessions, and you don't need to be a Python expert to create an MCP server. There are just two things we need to know before we can start building. The first is UV, a Python package manager. We will use UV to install all our dependency packages. The second is FastMCP. You can visit its website to learn more about what FastMCP is. The name is inspired by a very popular Python backend package called FastAPI. FastMCP provides a high-level interface library built on top of the original Python MCP SDK. The benefit is that it's faster to build with, it simplifies the development process, reduces boilerplate code, and is very Pythonic and beginner-friendly. Let's get started. First, use UV init to create a new project, then run UV add FastMCP to install FastMCP and all its dependencies. This will only take a few seconds. If you are curious, you can check the uv.log file to see all the dependency information. After installation, you will want to activate your virtual environment. Once you are inside the .venv environment, you can check the FastMCP version by typing FastMCP version. This will display the current FastMCP version as well as your Python version. Now, let's start with a simple hello world server. Before we do that, let's rename our main.py file to server.py. You can remove the main function and then start by importing the FastMCP class. Simply just typing from FastMCP, import FastMCP, and then MCP is equal to FastMCP. And you can put the name of your server. After you've created the FastMCP class instance, let's add a simple tool that performs the addition of two numbers. You can use @mcp.tool decorator to define a tool, specifying the input and output types. Next, let's create a resource. Refer to FastMCP documentation to see how to define a resource using @resource decorator. For example, you can copy the sample config data resource from the documentation and paste it into your script. Now let's return to the FastMCP documentation and see how to create a prompt using @prompt decorator. Copy the example code and add it to your script. You will notice that the prompt takes two input arguments, language and the task description. Both are strings and return a prompt message type as output. At this point, we have the three main building blocks in place: a tool, a resource, and a prompt. Let's try running the server to see if everything works. The last thing we need is a main function to launch the server. Copilot can even help autocomplete this for you, which is pretty handy. To start the server, check the CLI section of the FastMCP documentation. You have a few options. You can run the Python file directly, or if you want to use the MCP Inspector, you can launch it with FastMCP dev server.py. If you encountered an error about missing type definition for prompt message, make sure to import it correctly. Try importing prompt message and text content from FastMCP prompts. Once that's done, the server should start. It runs on port 6274. With the Inspector UI, you can use the web interface as a MCP client to explore the tools, resources, and prompts you've just created. For example, you can test the simple add tool by entering numbers, and it should return the correct result. You can also generate prompts by providing the language and the task description arguments and verify that the prompt is working as expected. Finally, you can check the resources which are formatted and ready for use by the LLM. Now that we've built a simple example with all three components, let's take a moment to dive deeper into what makes each of these building blocks unique. Anthropic has got a helpful slide that explains the key differences between tools, resources, and prompts. Understanding these different distinctions is important, even though it might seem a bit confusing at the first time. Tools are model controlled. This means the AI model decides when and how to use them during its reasoning process, so it's invoked by the LLM. Resources are application controlled. These are pieces of data or configuration exposed to your application. Prompts are user controlled. They allow users to provide specific instructions or context that guide the model's behavior. Not all MCP clients currently support all three building blocks. As of today, most IDEs, for example, VS Code, Copilot, Cursor, Windsurf, only support tools. if you want to see tools, prompts, and resources all working together, the best way is to use Claude Desktop. Now, I will show you how to set this up on Claude Desktop. Setting this up on Claude Desktop is straightforward. First, open the app and go to the Settings menu, navigate to the Developer section and click on Edit Config. All configuration is stored in a file called Claude Desktop Config. Open this JSON file with any text editor. Next, simply add the MCP server you just built to the configuration. You can specify how to launch your server just as we did before using the UV command or the MCP CLI. Once configured, you will see that under the Tools section, the Add tool is now available for the LLM to invoke. For example, let's try a simple addition. Enter 3 plus 90. The app will ask for your permission before invoking the tool. Just click Allow. The AI will then use the tool to calculate and run the answer. Now let's check out the other two components. Both prompts and resources appear under the attachment section. If you click on the data config, you can view the configuration data attached to your chat session. For prompts, clicking on a prompt will open a window asking you to input the required arguments, just as we specified earlier. For instance, you can enter Python as the language and ask it to write a scraper for Booking.com. Add a simple instruction such as just output the code. The application will attach this prompt to the request sent to the LLM. After a few seconds, you will see that the Python script for Booking.com scraper has been generated. The output will include key features, usage instructions, and important notes, all created by the AI using the prompt and resource attachment. Now we are ready to start our first real project, building a Confluence MCP server. This project will guide you through the complete process of creating a functional MCP server. I've created a repository called FastMCP course. You can find the link in the description below this video to clone the repository. In this course series, there are 3 projects in total. Project 1 focuses on building and setting up a Confluence MCP server integrated with VS Code, Copilot, and Claude Desktop. Today, I will guide you through Project 1 step by step. After Project 1, you will learn how to build and complete MCP server for Confluence to search, retrieve, create, update, and delete Confluence pages. Get the page children and ancestors for hierarchical navigation, manage comments and labels, list and navigate across Confluence spaces. As I mentioned before, you will need Python 3.10 or higher, and UV, the Rust-based Python package manager. First, make sure when you clone a repository, you specifically check out Project 1 branch. All you need to do is git clone -b project 1 and plug in the repository URL. Once that's done, cd to FastMCP course directory. You can just do code dot from your terminal to open up VS Code, or you can just open VS Code and choose the FastMCP course directory we just created. Once you are in there, there's one important thing that I need to mention to you, the system prompts. It sits under .github prompts. This is an important system prompt directory that Copilot will read before every conversation. So why it's important? Because what I have written here is a project guideline. In this project, we'll use GitHub Copilot agent to do all the groundworks for us. That includes setting up classes, file directories, and all the boilerplate code. So this guideline is critically important. It pretty much provides the guidelines for coding practices for the Copilot agent to follow. The API we will use is called Atlassian Python API. It's an existing package that we can leverage for all the API calls we need to Confluence. We also list out the folder structure, so when the code's generated by the agent, it will strictly follow what's being provided in the guideline without derailing to some overly complicated solutions. It also lists the environment variable names for the agent to follow. We also list out the error handling strategy and the test strategy. So the agent knows how to write the test codes based on this guideline. We've included the code examples from the FastMCP documentation with a special attention to the app context class. This class serves as a context manager for asynchronous processes. Wrapping our Confluence client into this context manager, this approach allows us to reuse the same client for multiple API calls without reinitializing it for every request. There's also a code snippet demonstrating how to create a search tool class, providing an example for the agent to follow. Finally, we've specified how tools should be registered with the FastMCP server using the recommended mcp.add tool function. Well, this might seem like a lot to process at first. Everything will become clearer once we start implementing the project. First, let's run UV-sync to install all the dependency packages based on our pyproject.toml file. This will ensure we have all the required packages before we start coding. Now, let's go to Copilot agent chat window, select the agent mode, and pick Claude 3.7 Sonnet. As our model, we will type our first prompt based on the project architecture we specified in the planning prompt MD file. Or to say, based on the project architecture, complete Confluence tools test directory and files configure.py and the rest of the project. Read the code example carefully. Make sure you understand it before creating the rest of the project. Now, once we hit submit, it will start generating the code for us. You can see it says it's starting to read those files that we pre-created for these tasks. It's reading server.py to understand the main functions, and it's reading the pyproject.toml to understand the dependencies and the project requirements. It's reading through README and the planning.prompt.md to understand the guidelines we set for the agent. Okay, it says it has got a good understanding of the project now and starts to make new directories. It's exciting. Let's just click on continue. You will see a few new directories have already been created by the agent. You can see it's now generating config.py file as well as the client.py in the models directory and the conference directory. It's creating the basic structure for our project following the guidelines we specified. The agent is setting up all the necessary components for our Confluence MCP server. In the config.py file, it's defining configuration settings that will allow our server to connect to the Confluence API. It includes setting up environment variables for authentication, credentials, and the base URL. Meanwhile, in the client.py file under the models directory, it's implementing the core client functionality that will handle the actual communication with the Confluence server. This is where all the API interactions will be managed. As the agent continues to work, it's also creating model definitions that will present Confluence data structures in our application. These models will help us maintain type safety and provide clear interfaces for working with Confluence data. This automated setup process is saving us a tremendous amount of time by handling all the boilerplate code and creating a new or well-structured project architecture. The agent is following best practices in implementing patterns that will make our code maintainable and extendable. Let's watch as it continues to build out our project structure, creating the various tools and utility classes we will need for our Confluence MCP server. The code generation is now complete. Let's clean up a few issues with the implementation. First, looking at the server.py file, I noticed that MCP lifespan handler is equal to app lifespan is incorrect. This needs to be fixed since our implementation uses the proper context manager approach. After reviewing the rest of the server.py file, everything else looks good. Let's examine the other files for potential issues. In client.py, AI has implemented exponential backoff for better reliability on API calls. There's also an issue with the response variable potentially being none, which could cause errors. Looking more closely, I see that multiple methods have the same issue with response handling. Rather than fixing each one individually, I will ask the AI agent to address this common error pattern. I'll just type something in like the response could be none and this none value needs to be properly handled in each function. The agent quickly identifies and fixes the response variable, handling in all relevant functions, ensuring we don't have non-reference errors. There's also an issue with a version variable that's commented out but being referenced elsewhere in the code, which needs to be addressed. Next, I examined the test files to ensure they are properly implemented. I asked the agent how the unit tests are supposed to be run in this repository. The agent analyzes the pyproject.toml file to understand the testing configuration and explains that we can simply run the test using uv run pytest command. I noticed that there's a reference to a request context in the test files, but this doesn't exist in FastMCP library. This is an error in the test code based on our server implementation. We are using an app context class for this purpose. I also encountered an issue where PyTest isn't installed as a dev dependency, which is preventing us from running the tests properly. I further fixed this one up by using UV to install PyTest as a dev dependency. Now let's spin up our FastMCP server by typing fastmcp dev server.py. It will spin up the inspector on port 6274. If you click on connect and click on list the tools, it will list out all the tools that we have built in our code repository. Let's try to search or get a page by page ID. Looks like we have encountered an error. Let's go back to our code and see what this error is. Now that we've discovered an error, let's go back to our code and fix it. When we examine the server.py file, we notice that there is a fundamental issue with the initialization order. The MCP instance gets created before app context definition, which means the Confluence client never gets properly initialized and picked up by the server. To fix this, we need to move the FastMCP instance initialization to be below the app context class definition. Second, add the app lifespan parameter to properly connect our context. After making these changes, we can use rough to format our code. Now, let's start the server again and see if our changes resolve the issue. After reconnecting the server, let's test our tools. If we go to Tools section, you can now see a list of all available tools. Let's try Get Page tool by providing a page ID. Now you can see when we run a request, we can see it has been processed successfully. If we toggle the body option, we should be able to see the complete page content. There it is. The content is in HTML format and it has been successfully fetched by our MCP Get Page tool. Now, let's just test creating a new page using our MCP server. Let's try the Create a Page tool with these parameters. Title, new page test, content, this is a new page. Use space key SD, which is the abbreviation for software development. When we hit run, we can see that a new page has been successfully created. Let's refresh our Confluence instance to confirm. There it is. New page test has been created by our MCP tool. Next, let's try another operation, creating a child page under an existing parent page. For this, we need to use the Create a Page tool again, but this time we'll provide a parent ID. Let's use the ID 6422529. We are getting an error. The input should be a string type. Looking at our tool implementation, it appears the tool is validating that the parent ID field should be a string, but we might be passing it as a integer. Let's go back to our code and check the definition of the get page tool. Indeed, we are validating the parent ID to be a string. To fix this, simply change that type of validation from string to integer. And we need to change that under client.py file as well. Okay, now let's restart our server to see if the change has taken effect. There we go. A new trial page has been created under the parent page that we specified. Let's go to Conference Space and refresh. As you can see, a new trial page has been created under the page 6422559. Let's try another operation, updating an existing page. For this, we will use the page update tool and provide the page ID 6422529. We will change the title to MCP from 0 to hero and set the content to project 1 as a simple update. Let's also provide a version comment to track our changes. When we click Run, we can see that the update has been processed successfully. Let's refresh our conference page to verify the changes have taken effect. Perfect. There it is. MCP from zero to hero. Our title has been successfully updated. Finally, let's test the page deletion functionality. We will use the delete page tool and provide the ID of the child page we just created earlier. After entering the page ID and clicking Run, the operation completes successfully. Let's refresh our conference space to confirm the deletion. As expected, the page has been removed from our conference space, confirming that our delete operation is working correctly. Next, let's test the get page children tool. To do this, we create a trial page under MCP from zero to hero and name it project 1. We add a single sentence as the example content and publish it. After grabbing the page ID of MCP from zero to hero, we run the tool. As expected, it successfully retrieves its trial page, project 1. Now let's test get page ancestor tool. This time we work in reverse. We grab the page ID of project 1, input it into the tool, and run it. The tool successfully retrieves its parent page, MCP from zero to hero. That's all done for page tools. Now we can move on to the search tool. Now let's test the search tool. We will start by searching for PRD in the software development space. Initially, the tool runs but returns an error stating that the query cannot be parsed. Let's investigate this issue. Upon reviewing the code, we noticed a problem. Here's a variable called CQL being used inside an if statement, but it hasn't been declared outside of it. This causes the CQL variable to always be undefined, regardless of how the logic is handled. To fix this, we declared CQL is an empty string outside of the if statement. After making this change, we run the tool again. However, the error persists and the query still cannot be parsed. Next, we check the logs for more details. The issue becomes clear when the CQL variable contains a simple word like PRD, it doesn't get enriched into a proper CQL statement. Instead, it remains as a plain text, which the Confluence API cannot parse. To resolve this, we modify the code to handle simple text queries. If the input is a single word, we prepend the text keyword to convert it into a valid SQL query. This ensures the query is properly formatted before being passed to Confluence SQL function. After implementing this fix, we run the tool again. This time, the search executes successfully, and we can see the expected results for PRD in the software development space. A few more tools, for example, get spaces, get comments, add comments, get labels, etc., that I'm not going to go through in detail right now. You can try them when you start working on your project. Now, what I want to quickly show you is the final integration with Core Desktop and GitHub Copilot. As I showed you before, you can configure Core Desktop by editing the desktop config file. Simply specify the directory where your MCP server is located. Make sure you provide the correct directory path in the config file and use UV FastMCP to run the server. Once the server is running, you can see the tools are available in Core Desktop UI under the Tools section. let's quickly try a prompt. For example, ask the AI to fetch pages that talk about a baby tracker from Confluence. The AI will likely ask for your permission first, then it will trigger the Search Confluence tool, which finds 3 pages relevant to the baby tracker app. Now, let's do the same on Copilot. First, go to the settings.json file and ensure you have specified the correct directory. After that, type another prompt. This time, let's ask the AI to create a new page named MCP Setup Guide. The AI will first search for the available spaces in your Confluence account. It takes a logical approach before creating a page. It checks how many spaces are available. Then it finds 2 spaces and determines that the software development space is the most appropriate for technical documentation. Next, it starts creating a page. Perfect. Now, let's go back to your Confluence workspace. Refresh it. As you can see, there is already a new page created called MCP Setup Guide. Cool, that's the end of the project 1. I hope you enjoyed it. Let's quickly recap what we've learned today. First, we set up the project using planning.prompt.md file located under GitHub prompts directory. This file provided a general guide for the AI to follow, including the folder structure, packaging, management, code quality standards, and coding practices. It also included code examples from FastMCP to serve as guardrails for the AI during the development. We used the GitHub Copilot in agent mode with the Claude 3.7 Sonnet model to generate the boilerplate code for the project. The project followed a well-organized folder structure. Server.py is the main entry point for our MCP server. Confluence directory contains the Confluence client class, which includes the client implementation, data models for Confluence objects, and utility functions for passing and handling API responses. Tools directory houses the tool classes. Each tool class is organized by functionality such as page tools and uses static methods to define the individual tools. This approach, recommended by FastMCP, keeps the code clean and maintainable. When registering tools, we used a simple register tools function in the main entry point to register all the tools from the different tool classes. This approach ensures the code remains simple and easy to follow. We also paid special attention to the context manager. The app lifespan function wraps the Confluence client in a context manager, ensuring we don't need to reinitialize the client for every API call. Additionally, we ensured the FastMCP server was initialized correctly and that the lifespan function was properly attached. Throughout the course, we saw how powerful AI tools LLM like Claude 3.7 can be in automating much of the development process. However, we also learned that AI can make mistakes, such as the issue we encountered with the CQL function. This highlights the importance of reviewing and validating the generated code to ensure correctness. Finally, we demonstrated how to integrate the MCP server with Core Desktop and GitHub Copilot, enabling you to use it seamlessly in your daily workflow. With this foundation, you are now equipped to build and extend your own MCP servers. Great job completing Project 1, and I look forward to seeing you in Project 2 and the following courses.